Okay, this session I'm working on PoorMansAnubis. Just like the other day, I'm working on getting, instead of the Rust implementation previously, it's now the C++ implementation that I'm working on to stream the data instead of loading it all at once and then sending it all at once. And I can say definitely after the session, the performance of the C++ version of PoorMansAnubis is better than before this session's work. So, unfortunately, this session is at least an hour and 30 minutes long. So, yeah, it's a big one. I'm focusing mainly on the direct IPv4 socket forwarding. There are two parts in the C++ implementation. One is just directly accessing an IP address at a specific port using TCP, expecting it to respond with HTTP. And it doesn't support SSL. The other part of the C++ implementation uses libcurl so that you could query a website that uses HTTPS. So libcurl is there to handle HTTPS stuff, queries. But if you're just protecting stuff on a local network, you can just specify HTTP : the IP address and the port after a colon. And it should work fine with that. That's all libcurl is for, just for when you want to use HTTPS. And this session, I'm working on the part that just does the work on the non-libcurl stuff. One thing I did notice that if I am to send data on the file descriptor to the client, I need to pass the file descriptor to the function that handles the response data. So by passing the thread data pointer to this function, I'm able to, reduce the arguments because some of the arguments are originally from the thread data struct. And second of all, the thread data struct has the file descriptor to the client, so I can send data with the write command or function, write function, directly to the client through this function that handles the request. Like the client requests PoorMansAnubis. PoorMansAnubis requests the destination responds back, and PoorMansAnubis responds to the client that same response, but somewhat processed. In this case, I'm using chunked encoding, which is streaming the data from the remote to the client. Normally, with chunked encoding, a server can just stream just data to the client. But in my case, I'm kind of using it as I'm getting data from the remote. And the remote could be sending chunked data themselves as well. So by the end of the session, there's support for the server responding with regular data and support for the server responding with chunked encoding. To be honest, I'm not entirely sure if that's properly being handled, the server responding with chunked encoding. But right now, my website is running the latest patches that I've made, and performance is better, and it seems to work even with some streaming resource. Like, for example, if I'm hosting an MPD stream, this seems to take up a thread, but it's able to stream that data. So I probably have to add a mention to this project about the number of threads that are allocated for use, being that a whole thread might be occupied if there's a stream being passed, like an audio stream or radio or whatever, internet radio, that kind of thing. The note I want to mention is that you should probably allocate more threads than you have cores, just to be able to handle such cases. I mean, on a Raspberry Pi 4, it only can support like, what, 4 threads? But it's not like each thread is using 100% CPU time, because it handles a lot of I/O, receiving data from the remote and sending the data to the client, and the writing and reading takes some time. So it's kind of either blocked on that and not using CPU cycles most of the time. So by using more threads than threads are available, it's more like making sure that every thread is actually actively doing something, because most of the time it's blocking on I/O. And this is different from non-blocking I/O, which I'm using. I'm talking about waiting for an input-output operation to finish, and that takes longer than a regular busy loop, for example, or something like that. It consumes less CPU cycles than doing actual, like, calculating work. I/O, that is. So, to support the change I'm trying to make, I have to heavily refactor the existing code in the C++ implementation. And I'm kind of like retrofitting like parts of the code, commenting out parts of the code, simplifying function calls by using the thread data struct, stuff like that. Since the C++ function, the do IPv4 forwarding function, takes the data struct, thread data struct, it doesn't need to return the file descriptor to the remote anymore. So it returns void and sets it itself in the data struct that is passed to it. Like I've mentioned before, it's better to pass a pointer to a struct than a pointer to pointers like I did in earlier projects, other projects. Because if you pass a pointer to an allocated struct, at least you know for exactly sure what elements you're using. If you were using the dirty fix I did in my unit test, having a void pointer array of pointers, a single misindexing of the, like, if you get the order wrong or if you use more pointers that are available than they're allocated or less, you can cause problems with like invalid pointer casting to a type that isn't actually that type. Using the struct ensures that when you access a member of that struct, it's exactly what you expect it to be, as long as the pointer of the struct is actually the type of the struct that's being passed. This project happens to use Clang format as the formatter, which is handy as long as you don't forget to use it. If you're using Git or Subversion or whatever for your version control system, any change to your code will be logged. Or not logged, it will be just saved. Every change is saved. And if you only have formatting changes, you might lose consistency with your version control system history. Because, like, if you use git blame, it may show that a line was changed because of a formatter, and you don't care about a line changing because of the formatter. You care about the line changing based on a commit that someone made, based on whatever patch. So As long as you remember to format your code as you're adding it, there should be no problems. So there's this weird quirk I noticed in my cleanup handler. I only need to check the pointer value, or the pointer itself, not the value the pointer is pointing to. For some reason, there was a third check on the value of the pointer itself. And I only need to check the pointer and the subpointer, the inner pointer. As a double pointer, you check the outermost pointer and the one level in pointer, and 2 levels in is the value. Yeah, pointers are really confusing at first, but if you can figure out pointers and memory management, you're basically good to go with programming in C. Just, there's a lot of gotchas you have to be aware of. Note that this project is C++, but you can use C stuff in C++. For example, Rust, you cannot directly use C functions because every C function is inherently unsafe. The Rust compiler cannot make the same guarantees with C functions. So any use of the foreign function interface, you have to use unsafe. Rust is therefore kind of works with C code if you want it to, but you have to use it with the unsafe keyword. C++, on the other hand, it's like a superset, and C can be used as a subset of C++. Or in other words, you can write C in C++ and it would be mostly okay with it. There's some gotchas with it. Like if you have a struct declared in C and you parse that with a C++ compiler, it might have problems with linking when you compile the program later on. Because when you compile a code that has a struct or a function in C with a C compiler, it doesn't mangle the name of the function or struct. C++ and Rust, every time you compile it, every function name and every class and struct name is kind of mangled with an internal format. It's the same type as you expect it to be, but like how code changes into really gnarly assembly, if you look at the assembler, the names of functions and structs and stuff like that also are changed a bunch. With plain old C, these functions don't get mangled as much, but the mangling behavior is different between C and C++. That's why some C code has an if def C++ or whatever, and it has an extern quote C quote, that kind of stuff. That tells the C++ compiler to use the C compiler rules for mangling a struct or a function name. So as long as if you have code that you want to use both in C++ and C, when the C++ compiler is running, the C stuff should be surrounded with an extern C. But if you're using the C compiler, you don't really have to worry too much about it other than not using C++ stuff. In other words, the interop between C and C++ is not that difficult, but that's a thing you have to be aware of. So right now I'm dealing with this comment code about what if this PoorMansAnubis is receiving chunked encoding data from the remote. I need to check for the 0 carriage return new line, carriage return new line, so that I know that the remote is done sending its data. Because if I don't know if the remote is done sending its data, the client will hang waiting on PoorMansAnubis, because PoorMansAnubis is waiting on the remote until a timeout happens. This is actually a bug that I encountered late in this session. So the check here I need to make is that when I receive data from the remote, if it has a specific pattern of characters at the end of the buffer, and the pattern for ending a chunked encoding body is a 0 and all that stuff. Naturally, I have to ensure that the buffer contains I have to ensure that I'm not going out of bounds with these array accesses. There's a risk of an underflow here if read size is too small. As long as I have this check though, there's no risk. The read size greater than or equal to 5. So here I'm ensuring that the headers sent to the client contains the key transfer encoding and the value chunk, as that is the heart of having this chunked encoding process, sending a stream of data from this remote to the client. The logic in this code is a bit convoluted, but I have some flags and I have some loops. The before content flag just tells me if I'm done parsing the status line and headers. As an HTTP 1.1 request and response is basically a status line or a request line, and then a bunch of headers, and then the body of the request. Naturally, client requests are usually just the request line and then the headers, like something like slash get, like a get request to the root of the URL, and then the headers could be like a cookie if it has a cookie or something. It's weird, but long story short, the response and the request and the response follow a similar format for HTTP, at least for HTTP 1.1. Every browser is compatible with HTTP 1.1. I think at least every browser is. There is such a thing as HTTP 2.0, but it's kind of more complex. I don't intend on supporting that because it is a lot more confusing. I think it uses some kind of like HTTPS based encryption built into the protocol, but I'm not so sure. For now, HTTP 1.1 serves well for my purposes, and every browser basically supports it, so there's no real reason to go to a more advanced protocol when I could use 1.1, which is a lot simpler than 2.0, I think, last I checked. This is HTTP I'm talking about. HTTP is a protocol. HTML is the file type. Yeah, it's confusing. But yeah, it's confusing sometimes. And an HTTPS is HTTP but wrapped in encrypted packets. Since PoorMansAnubis sits between the client and the remote, if you don't use a reverse proxy with it, it can't use encryption. So what's actually going on is I'm having Nginx sit in front of PoorMansAnubis. The client connects to the website. The website is being handled by Nginx. It hands over the request to PoorMansAnubis, and PoorMansAnubis does its thing and then requests its configured remote, which might be another location handled by Nginx or a local server that's simple using HTTP. In other words, you should be using PoorMansAnubis through a reverse proxy, which is just some kind of handler sitting in front of it so that it can use HTTPS because of the handler. Or in other words, have Nginx set up with HTTPS with certificates and all that, and have it request to PoorMansAnubis to request elsewhere to be protected from most scraper bots. I think I mentioned this in the README for this project. Again, I'm using non-blocking I/O for my file descriptors for the remote and for the client. Basically, blocking I/O is if you read with blocking I/O, it's going to block on the read function, and the program will wait for any data to be received, and then you get the result. Non-blocking I/O is when you call read, and if there's nothing to read, it immediately returns with error number set to E again, or E would block in this case. Instead of using a separate thread to handle blocking I/O, I use non-blocking I/O to handle it. It's more of a preference if you think about it. Some people it's simpler to just make a new thread and read or write with blocking I/O. The problem is there's overhead with threads, but usually if you use the non-blocking I/O, you can use just your current thread. You just need to add more stuff to handle the function returning with non-blocking I/O status. For example, the server did not accept the data, so you have to resend it again a little bit later. If you do a busy loop with non-blocking I/O, it's probably not gonna. You're basically doing blocking I/O, but it's busy waiting. Or in other words, if you do a brief infinite loop trying to write over and over again with non-blocking I/O, you're better off putting a sleep inside of that loop, because for the reasons that the first write didn't go through, it still might not have resolved for that immediate next cycle. And in computer time, one cycle is very fast. You basically, how processors are rated in like 4.5 gigahertz, 4 gigahertz. That basically means that 4 billion times a second is a single CPU cycle. Not million. A megabyte is a million. A gig or M is a million. Gigabyte or gigahertz, that's in the billions. So, in other words, if you have a thread, or if you have a loop that's busy waiting, a infinite loop that doesn't sleep at all, almost every single CPU cycle will be wasted constantly trying to go through. I mean, if you need it to busy wait for something like an atomic lock, or a mutex, I guess you have a lot of low latency stuff that you need to do, but for the purposes of my program, it sleeps for like 2 milliseconds. That might be in the thousands or millions of cycles. Well, considering when 4 billion cycles in 1 second, waiting for 2 milliseconds is like turning that into 4 million cycles past. Computers run very fast, long story short. And if the remote is not responding with a read or write, if it was blocking I/O, it would just wait for it to go through, which is basically the same thing if you're doing a loop, like I said. If you're doing other stuff on the side, then your loop is more efficient, I would say. Like for example, you did non-blocking I/O, you did a write, server did not accept the write, so E again or E would block is set to the error number. You can do other stuff and then send another write function call to the remote again after you've done the other stuff, while basically you can process other data while waiting for the write to go through. It's kind of similar to green threads or coroutines in a sense. I don't know, I just really prefer to use non-blocking I/O over blocking I/O. Since I'm planning to, well, I've already done it, but in the session, I'm using the function that handles the request to directly write to the client. I need to write the status line at some point in the headers as well. So when I know that the content is next to be parsed, that is when I start sending the status line and headers to the client, which is this part I'm working on in the session right now. These write and read function calls return a negative number on error. It's usually just -1. Even for non-blocking I/O, it returns -1. And the distinction is that the error number global number is set to E again or E would block to indicate that the non-blocking IO remote didn't accept the data yet, or didn't have data to be given to you if it's a read. If you get a 0 returned from a read or a write, it usually means that the opposite side of the connection closed the socket, closed their side of the TCP connection. And if it's more than 0, that's just the size of the number of bytes that were read or written, as far as I can remember. I think the fopen and fclose and fwrite and fread is a bit different. It's part of the C standard library API. It's a bit more documented differently. I'm not quite sure if those things support non-blocking I/O. What I do know is it has functions to check for end of file and error. I just basically use raw Unix sockets with integer file descriptors. Fun fact, file descriptor 0 usually is standard input, file descriptor 1 is usually standard output, and file descriptor 2 is usually standard error. So if you see some weird stuff being printed in your terminal and you're working with integer file descriptors, it might be you're accidentally writing to a standard output or standard error. Another weird quirk I ran across once. But usually when a program starts, those three numbers are usually standard input, standard output, standard error. It's kind of almost hard-coded, but it is the first three file descriptor streams that are available. Usually. At least in Linux, as far as I can tell. So here I contemplate copying data from within a buffer to the first byte of the buffer. But I looked it up and it's undefined behavior to use memcopy when the two buffers are the same buffer but at different indices. In other words, if there's an overlap in the data being mem copied, it's undefined behavior. So if you need to do something like that, you're better off making a temporary buffer, writing to the temporary buffer, and then back to the original buffer that you need to write to. And undefined behavior in C literally means anything can happen, and usually it's not what you want to happen. I mean, the compiler can literally just do whatever it wants to, since it's undefined behavior. And you should never depend on undefined behavior for anything, because it's prone to change, and undefined behavior stuff is worse than unsafe in Rust, to be honest. A good program never has undefined behavior. So, it's not really the same as unsafe in Rust. Unsafe in Rust is just the compiler cannot guarantee anything for you. In C and C++, undefined behavior is just, if you do this, bad things will probably happen. They're not quite the same, but they're kind of similar in how strict they are. Every header line in the header section of an HTTP protocol response or request needs to end with a carriage return in a new line. The header section ends if there's two carriage return new lines going on. That's how it can tell. Note that I'm not using C strings or anything like that here. If I include a C string null terminator, it's not part of the specification of HTTP, so that would be basically malformed data if you put a null byte in the middle of all that. Unless, of course, the header actually includes a null byte, which I don't think it should. I don't think that's allowed actually, but basically the string, the C++ string, you can get a C string out of it, but I just need the string itself, and it can tell you the size of the string itself with a function call. And here is the ending carriage return new line, ending the header section of the request response. Or actually, this is writing to client, so this is the response to the client. Okay, so I think I did a mem copy from buff data to buffer data with an overlap, possibly. I need to fix that. There's no guarantee that it's not going to overlap the way it is written. As part of the chunked encoding transfer, I need to send the hexadecimal number and then the chunk. The hexadecimal number is the size of the chunk that follows. This is the inspiration for the chunked encoding in Simple Archiver, the way HTTP handles chunked encoding. The difference is, in my Simple Archiver, it just uses a decimal number, while in HTTP it uses a hexadecimal number. And I use just a single new line in Simple Archiver, but in HTTP it uses a carriage return and a new line, \r\n. So this is a potential buffer overflow situation when you want to append to a buffer. The way I fix it is I go back to the definition of the buffer itself and allocate more memory. Just 2 more bytes in my case. I make sure that when the buffer is read into, that it uses the size constant, not the actual size of the buffer. At first I used -2 here, but I changed that to the constant. I should probably log the error number values whenever I get a right error. That's also another thing I should do. Right now the log is just, there was an error. But if I print the error number, I would know a little bit more, it would be a little bit more informative of what the error was. Here I return an error if there was a partial write. After the session, I handle the partial write to ensure that it writes all of it, because that was breaking things. I handle the partial write by ensuring that all of the bytes are written using an offset variable. It could be an exercise for the watcher, I guess. You could think, oh, there's a partial write, how do I fix this? And my code after the session has the fix for that. If you want to give yourself a mental exercise, you can just think about that and then look up the code later to see what I did to fix it. I think I've said much, though, about how I fixed it, though. The end of a chunked encoding body is a 0 and then that stuff. I think I mentioned this already. I actually encountered a bug where this doesn't occur, and the client waits until a timeout value passes. Commenting out this chunk of code turns out to be a mistake. That's one of the first bugs I run into when testing. I can safely static cast write return to a positive only type, an unsigned type, because the if statements before it handle the negative and the equals 0. I remember when I first tested this, the first bug I encountered was that the verification wasn't even working at all. And that was because of the code block I commented out. It's actually being used by that part of the program. So I need to conditionally call that block. It takes a while for me to realize this though. I'm just rechecking the code to figure out why the challenge response isn't working. Because I didn't touch that part of the code for some reason. Well, I was only handling the response after verification, so it puzzled me as to why that wasn't working. And basically, the commented out code was being used by that part. Yeah, for a while I keep not figuring out why it's not working. The error I see is the challenge response isn't even showing at this point. So here I finally used a flag to set the block to only execute conditionally. If it's not being, if the new stuff I added isn't run, otherwise run this block. Now that I've got the challenge response working, there was another error that I discovered. I had to use Wireshark to figure it out. Unfortunately, asciinema didn't catch me using Wireshark. Long story short, PoorMansAnubis was sending the chunked encoding, but it wasn't sending the zero character return new line after the chunked encoding. So the browser was hanging, waiting for that to occur, but it never happens. So I have two possible things happening from the remote. Either the remote tells me the full size of the data it's sending, or the remote is doing chunked encoding. And most of the time, the remote is sending the full size of the data being sent, with a content size and then a number, and then that number determines the size of the data that's being sent. Silly for me to use printf stuff when I'm using std format here. I think at this part I'm thinking about how to how to check for the end of response from the remote. And here where I realized I removed the code that handled receive content size properly. Because once I've sent receive content size data, that should be the end of the stream from end of the request response from the remote. I've gotten that inner if statement a little bit backwards. Value should be greater than or equal to read size, not the other way around. So I think when I did these tests, the browser was still hanging for the response to be completed. And I mishandled the receive content size variable. So as you can see, it printed an obscenely large number. That is an integer underflow. If you subtract to an unsigned integer more than its current value, it wraps around to its maximum value. And that's a sign that I messed up handling that value. Notice earlier I incremented read size twice by 1. The actual data is the read size minus 2, so I was overshooting it by 2 values, or 2 units, that is. 2 bytes. I'm not sure if the client returned, but if I'm making changes, then if I'm making changes now, then I think at the time of the session, it still wasn't stopping the request properly. That single goto allows me to reuse that code without having to rewrite it. So I think at this point in the session, everything is working as it should. I do make a few changes afterwards because of spurious errors that happen. Mainly the partial rights bug showed itself again after the session. So I had to ensure that partial rights would resolve to actually writing everything eventually. I guess the trade-off for non-blocking I/O is that partial writes can happen. That particular port is hosting my MPD stream locally. So with the changes introduced in this session, it is now possible to have PoorMansAnubis work with an HTTPS or HTTP stream. Sorry, not HTTPS. A regular HTTP stream should work. It will occupy a thread though. So if you expect to be streaming a lot of stuff through PoorMansAnubis, you may have to increase the thread count. So that's basically it. That's the end of the session. That's what I do left is remove some commented out code that is no longer necessary, and then do git commit and push. So since that's basically it, thanks for watching.